Okay, here's RC circuits.
The pause.
Okay, so RC circuits stands for resistor capacitor circuits. Okay, so yeah. So here we go.
As we add electrons to the first metal plate, an equal number of electrons leave the second metal plate.
Okay, so we got a capacitor.
After a certain number of extra electrons accumulate on the first plate, they will repel any new electrons trying to enter. The first metal plate has developed a net negative charge, and the second metal plate
So
has
that
developed an equal and opposite
instead of
net positive
force,
charge.
they should use voltage.
We can cause this equal and opposite charge on each plate to be larger by applying a larger external force.
Larger voltage, external voltage from a battery. It's more pressure. And see how the pressure builds up on the
If we
plate?
remove the external force we are applying, the extra electrons in the first metal plate will continue to repel one another.
So this is a capacitor discharging.
We have now returned to our original condition where the net charge on each plate is 0. The two metal plates are what we call a capacitor.
Okay, so here's an RC circuit.
Note, voltage is shown upside down in this video because the blue arrows will show electron flow.
Okay, so you have a voltage drop when that circuit is
By
connected.
connecting the capacitor to a battery as shown, the two plates have developed equal and opposite charges.
So
If we then connect the capacitor across the light bulb, all the extra electrons in the negatively charged plate will move to the positively will show electron flow.
okay, so when it connects here, we have a voltage drop across the resistor. There's no voltage drop across the capacitor yet because it's not charged. But as this becomes charged, there builds a voltage across that. Okay, so watch what happens to this. Where you have a big voltage drop here and none there, but over time, they flip-flop. So at that point, there's no flow because the voltage across the capacitor matches the voltage across the battery.
The capacitor to a battery as shown, the two plates have developed equal and opposite charges. If we then connect the capacitor across the light bulb, all the extra electrons in the negatively charged plate will move to the positively charged plate through the light bulb.
Okay, so the capacitor is now the battery. Voltage drop across the resistor matches the voltage drop across the light bulb. It's actually a voltage gain with the capacitor now.
If we use multiple batteries in series, then we can force the two plates of the capacitor to develop larger amounts of charge. When the capacitor is charged, its voltage will be the sum of the voltages of all the batteries.
Okay, so now the capacitor is the voltage gain and the resistor is the voltage drop.
Voltage will cause the light bulb to stay on longer when the capacitor discharges.
So it's like a temporary battery.
Now suppose that we increase the areas of the two metal plates. This increased area allows us to push more extra electrons into the first metal plate.
So that's your
And remove
charge.
more electrons from the second metal plate.
Increasing
Without applying a
capacitance,
larger external force.
because you can have now more charge for the same amount of voltage, same amount of pressure. That's capacitance.
When a larger capacitor is connected to our battery, it'll take longer for the capacitor to charge to the voltage of the battery.
Does that make sense? It takes more time.
Although the final voltage is still equal to the voltage of the battery, for a larger capacitor, this voltage represents a larger amount of charge on the two metal plates. The larger capacitor will take longer to discharge through the light bulb, thereby allowing the light bulb to stay on longer. Suppose that we add a special material in between the two plates.
Like a dielectric?
This material does not allow any particles to flow through it, but it contains molecules that change their orientation based on the charges of the two plates.
Polarize?
These molecules exert forces that attract more electrons to the negative plate and that repel more electrons from the positive plate. The presence of this material has the exact same effect as does increasing the areas of the two metal plates. This allows the two plates to develop larger net charges for the same amount of applied voltage. We say that we've increased the capacitance of the capacitor. There is also a third way to increase the capacitance of a capacitor. This is by moving the two metal plates closer together. Because the two plates are now closer together, they exert greater forces on each other's electrons. This attracts more electrons to the negative plate and repels more electrons from the positive plate, allowing the two plates to develop larger net charges for the same amount of applied voltage. This has the same effect as inserting the special material and as increasing the areas of the metal plates. To create the largest capacitance possible, we want to make the areas of the plates as large as possible, insert the special material in between the plates, and move the two plates as close together as possible. The larger the capacitance, the more energy will be stored for the same amount of voltage. Much more information.
Okay. So, hopefully that gave you conceptual understanding of what's going on in an RC circuit. So we're going to start with the idea of the capacitor has already been charged, and we're going to light the light bulb. Okay? Because it's easier mathematically. And then we'll go to charging a capacitor, which is harder mathematically. Okay? So what we're starting with original, like in our initial voltage across the plate. It's been charged, okay? And there's a certain amount of charge. So the ratio voltage, like your capacitance is charge over voltage, okay? And there's no current. We're about to close the switch. Okay, so that's our stage for this experiment. Everybody good with that? Okay. So what we're gonna go for is we want expression for current as a function of time. Okay. So the catch with this is okay. I guess before we do the catch, we're going to employ Kirchhoff's loop rule. So the capacitor becomes the voltage gain, and the resistor is going to be your voltage drop. Current's going to go out of positive into negative. Okay. So at any moment in time, this is always true. If voltage across the capacitor is equal to the voltage drop across the resistor. Good with that? Like that is like a, oh dear, better run out of battery. So that's our foundation. Kirchhoff's loop rule. Okay. Now the killer is that the voltage drop across the capacitor is not constant because the charge on the capacitor is not constant. Nor is the voltage drop across the resistor constant because the amount of current flowing through that resistor is changing as a function of time. Good with that? Okay, so the lowercase variables signify they're going to be changing. Okay, so your charge is changing and your current's going to be changing. Okay, so this gets, we're accounting for a negative sign here. So if I mess this up, it's because of this thing right here. So we are saying that the current, the resistor current is the rate at which charge is removed from the capacitor. So current is the rate at which charge is going by a certain point every second. Okay, we have this negative here because we're gonna make a relationship between the current through the resistor and the charge on the capacitor. And so we're going to represent the current as the rate change that the charge is leaving the capacitor. So that's why that negative is there. Okay. Okay. So here, everybody good with this so far? Kind of established this. Okay. We're going to represent the current as the negative derivative, the time rate change of the capacitor, of the charge coming off of the plate. Okay. And then what we have, we are going to put the RC over here. Sorry, just the R over there. And these two cancel out, so we get positive. So at this point, we're doing like air resistance. The what's that term? Method, separation of variables. So we're going to put everything with Q on this side. So we have Q over here, And everything else we're going to bring over here to dt. And the negative is still there. This derivation is in the realm of possibilities of what you would need to do on a free response test. And I will let you know, I would say 80% of the free response questions about circuits are RC circuits. Okay, so we're going to spend a lot of time on RC circuits. Okay, good with that. Okay, so we get to this point here. We need to integrate, and our limits of integration, our charge is starting fully charged. We have a fully charged capacitor, and we're going to some temporary amount of charge. We don't know what. We're stopping that at some point in time. Okay, and over here, we're going from dt, so we're starting at 0 times 0 when the switch is closed, going to some arbitrary amount of time. Okay, so when we do this, we get natural log of q, q minus natural log of q, yes, absolute value, yada, yada, yada. Okay, and you get negative dt t over rc. You okay with that? Sorry, let me just do this. Be better teaching better. Okay, so that becomes natural log of q over q naught equals negative t over rc. Natural log it, e to the whatever, okay, and then bring that over, so you get q is equal to q naught e to negative t over rc. Is that big enough to read in the back? Yeah, you guys, your eyes are young. Okay. So, often we're going to condense R and C together as a time constant. So we reduce the RC as that the time constant is the rate. So RC, the units on that's kind of funny. So you have ohms per farad. So an ohm is volt over amp. Farad is a coulomb times a volt. Okay, and a volt is a joule per coulomb, and an amp is a coulomb per second, and coulomb Right? No. That's volts, right? That's volts. I should have canceled that out way long time ago. Sorry, backing it up. Farad is a coulomb per volt. You guys should have caught me on that one. Okay, that kills that. So you have a coulomb over amps, which is a coulomb per second. What? It's in seconds. It's how quickly it's a measure of how quickly the capacitor discharges or charges. It's a time, like it's counter thing. Okay, which is dependent upon your resistance and the capacitance. The higher the resistance, the slower current is going to go through there. The bigger the capacitance, the more charge can be held on the capacitor. Good with that? That is your charge as a function of time equation for charging a capacitor. Nope, just kidding, discharging a capacitor. Okay? So, it makes a shape like this. Okay, so if you ever have an equation that's in this format, it's going to make a shape like this. Okay, it's kind of like an exponential decay curve, half-life type stuff. Okay, I would not worry about memorizing these. Typically, after 10 time constants, that's a sufficient amount to say that's discharged fully. Technically, it's approaching zero, but let's be real. It's close enough to, like, 10 time constants, you're good. Discharged. Okay. Good with that. All right. So if that's the charge on the capacitor as a function of time, the voltage, let's see, charge of voltage or charge. You can say this is the voltage. Think. V. That's charge over. Nope, I just want that. That is capacitance times the voltage across the capacitor equal to the capacitance times the voltage across the capacitor, the initial one. The capacitance doesn't change, so you end up with this. You have the same shape for voltage across the capacitor. And therefore, so this is across the capacitor, because loop rule is a thing, the voltage across the capacitor is equal to the voltage across the resistor. One's gaining, it just does this. The voltage across the resistor, because the voltage across the capacitor is equal to the voltage across the resistor, due to one's a voltage gain and the other is a voltage drop. Same shape. And we know that because that's the case, so we have the same voltage across the resistor. The current, therefore, when we do I times R equals, I'm going to make that a lowercase, I times IR. Okay. The resistance doesn't change. So we get this expression for current. Again, it has the same shape. Asymptote at 0. Yep. Do that. Okay. So when discharging, all your variables are going to have this format of a graph and this format for the equations for all the variables. It's kind of nice. I like that. Okay. So that's the discharging. Here comes charging. Oh, just kidding. There's that graph. Okay. This is probably like a free response part lab question. I could figure out the time constant experimentally if you weren't given R or C, but you could if you had a function of time or charge as a function of time. I mean, that's kind of like your Q naught. So you know this, you know that. E negative T tau. Backing this ship up here. Seems like a not very experimentally. That's not very experimental. I'll just go until it's like close to 0, and then divide that by 10. Okay. All right. Charging the capacitor. So here, this is our voltage. Our battery provides the voltage gain. Okay. So initially, there's no current in the across the resistor or in the resistor, and no charge on the capacitor. Okay. So, but when you close this, right at the beginning, the empty capacitor acts like a wire with no resistance. Okay, does that make sense? So it's like there's nothing that prevents, okay, from a reality point of view, let's say electrons are coming off here, electrons are coming here, hitting this, knocking these off. There's nothing that's like preventing that process from happening right at the beginning. It's like, okay, sure. So you get current going. But over time, this is going to get charged up, producing a voltage across here. Initially, there's no voltage across here. Over time, this is going to build up. And so it's like they're getting crowded in here. It's like, oh, so that process slows down. You good with that? And so current is going to be decreasing. Does that make sense? Still decreasing the current. Okay. But so the current behaves like this. So we still have this equation for current as a function of time. That still holds true even when we're charging. Okay. But as time goes on, this is getting filled up. Okay. And the full capacitor at the end, let's see, at the beginning. Okay. Full capacitor acts like a broken wire at the end. Preventing current from going. Does that make sense? Okay. And so what happens to the charge ends up, initially it's like, yeah, because, okay, check this out. Current is the time rate change of charge. Initially, you get this surge like, whoa, yeah. So the slope of this is greater. As time goes on, the slope ends up going to zero because the current's going to zero. How are we doing there, Jared?
Would any of that change if, like, the resistor and the capacitor were like flip-flop in order?
Great question. No, that would not change at all. Great question. Okay. Good with that?
Would the capacitor on the top before the switch is closed not charge a little bit if like the positive voltage from batteries touching it?
Yes. Yep. They would. But we're going to consider that zero. Okay. So here we go. This is where I give you a head start and then I come up behind you to make sure we're doing all right. So I want you to write Kirchhoff's loop rule for the circuit. Okay, after the switch is closed, but before it's fully charged, like sometime in the intermediary transition steps. What is Kirchhoff's loop rule going to be for this circuit while charge is still flowing? Do what? It is a perfect battery. So put a lowercase letter for variables that are changing. So you're going to have a voltage gain from the battery. You're going to have a voltage drop from the resistor. And because this is becoming charged, this is going to be a voltage drop across the capacitor. So this is becoming positive. This is bottom plate becomes negative. So as we progress along, it's like there's a voltage gain. We're going from negative to positive. Here it's a voltage drop. The current's going this way. Voltage drop. And here we're going from positive to negative. That would be a downhill ladder or upside down ladder. How are we doing? Okay. Now, is charge being added or taken away from the capacitor? Added. So are we going to have a positive derivative or a negative derivative for the rate charge? It's going to be positive because we're adding it. Okay. Good with that? Okay. This is me. All right. Divide by R. Let's do that. Divide by R. Oh, that's not R. That's a EMF. All right. So we got EMF over R minus I minus Q over RC. 0. Bring everything with DT on the left side. Crap, it's already over there. Everything else on the right side. Okay. Oh, wait a minute. Rewrite the equation. We're making that dq over dt. There we are. Good with that. This negative came from the fact that we had a voltage drop. Okay. Everything with okay. This is me coaching myself, if you couldn't tell. I know, right? I kind of want that over there, right? On the right, so we can get an expression of time constant. By whatever's left over on the right, the part with Q in it, so that it's on the left. So ugh. Factor out an RC that says factor out a negative RC. Nope. 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 That's it. That's just okay, so I'm going to get rid of the negatives. And then, so we get an expression with time constant. Okay, that's our. Okay, divide by whatever is left over on the right. All right, so we're going to do this. So this is 1 over, which that's the charge of a fully charged capacitor, yes? Ugh, that's full. One over tau, yes. dt. Is everybody okay with that? The 1 over tau? Whew. I'm going to integrate from it starts 0 charge and goes to some intermediate charge. And this starts at time 0 and goes to some intermediate. Okay, so I'm going to go natural log of Q naught minus Q minus natural log of Q minus 0 is equal to, where, yeah, good call. Which what do we tell?
Just multiply that here by -1, so negative first and positive second.
So switch these positive and negatives?
I think.
I'm okay with that. I just jumped. Yes. So dq is -1. Yes, good call. Man. Bless you, bless you, bless you, bless you, bless you.
Good call.
All right, so we'll go doot, doot. Yes. And then T over tau. Yes. On that side. Okay. And then we go Q over Q naught minus Q. Yes. Natural log. Q. I hope this works. It'd be a shame if we go through all this and we don't get it to work. Oh, where's my negative? Ugh, I need a negative. Need a negative. I need a negative. Shoot. I need a negative right here. This needs to be negative. Where'd that go? That needs to be negative. It was there. We killed it right there. Shoot. Voltage drop, voltage drop. Yes.
What if you, instead of canceling out the dq with the -1 in the front, cancel it out with the difference? So it becomes positive q, negative big Q.
Oh.
Then I'll swap that in.
Don't cancel. I need to put that on there. Okay, I like that idea. Ah!
negative sign for the other one, it cancels with the negative q and makes the other one become a minus. Yeah, you keep the negative on the.
Keep the negative.
Keep negative on the t.
And then make this. Then make this q over that. Yeah.
Yeah, that's right. Just
Yeah. And then that flips.
And that goes to. Ooh, I don't know if I like that though. Does that work like that? Zero minus q. That would flip that too. Oh dear me. Okay. We're rolling with it because that needs to be negative. What?
It wouldn't be negative due to use of
It wouldn't.
No.
God. Okay, so that's. Oh, is that us? Stink. So here's your Indian equation. This is what you should end up with. Q is go. Q not like full. 1 minus e to the negative t. That gives you this graph here. Goodness gracious sakes alive. Hey, thanks for tilting my computer. I'll post a free response homework that'll be due on Friday.